Thank you very much for the introduction and for the opportunity to give a talk here within the OWLE seminar series. So as Andreas already mentioned, I will talk about particle accelerator optimization using densely connected and invertible neural networks. And this was a joint work with Renato Bellotti and Andreas Adelmann. I will start with the general problem formulation, and then I will show you the neural networks we are using, and I will present the results for two showcases later. I guess for the audience here, I do not need to give an introduction to particle accelerators, since you are all aware of their importance for science and technology. There are different types of accelerators, as you can see here on the image of the Paul Scherrer Institute, which is, by the way, the only place worldwide with this variety of accelerators using photons, neutrons, and muons under one roof. One thing all accelerators have in common is that one is first interested in how an accelerator should be designed, and further, how good operating points of accelerators can be found. And therefore, models of accelerators are needed. And these models can, for example, depict the whole accelerator from the machine settings to the beam response. And what is done mostly is that physics-based models, like the object-oriented parallel accelerator library OPAL, are used to simulate the accelerator in the forward direction, so from the machine settings to the beam response. And for the inverse direction, mostly optimization algorithms are then used in combination with those physics-based models. And the problem we are facing here is that the physics-based models like OPAL are high fidelity models, very nonlinear, and they are computationally very expensive. So one forward simulation could last a few minutes or up to hours. And if you think of using, for example, a genetic algorithm, then for the optimization with, let's say, 1,000 generations, it's not really feasible, or it would last very, very long. So the idea was now to replace those physics-based models with a machine learning model, with a surrogate model. And what I will show you today is that we will introduce two different models, one forward surrogate model that describes the accelerator from the machine settings to the beam response. And I will introduce a second surrogate model, which is invertible. So you can model the forward and the inverse direction. And we will further use those models then for optimization. So the concept or the idea we are following is this one. So first, we need to create some training data. For that, we use the OPAL library, where we plug in some machine settings and get the particle beam response. And then we use both the data to train our surrogate models. And then we will use those models on the one hand for prediction. So both models can be used to predict from the machine settings the beam response. And the invertible surrogate model can also be used to predict machine settings from a desired beam response. And in the next step, we will use the surrogate models for optimization. So we want to optimize the beam response and get optimal machine settings. Okay, so now I will present you how our models look like, and I will start with the surrogate forward model. So for that, we use a simple, densely connected neural network, where we have as an input here, the axis are the machine settings, and as an output, we have the beam properties, and we have some hidden layers in between. And the new thing about our surrogate forward model is that it can describe the particle accelerator quasi at any longitudinal position along the entire accelerator and not only at one position, as it was already done in literature before. And so for the invertible surrogate model, we use so-called invertible neural networks that were introduced by Addisone. And so the main building blocks of those invertible neural networks are affine coupling blocks followed by some permutation layers. And those affine coupling blocks are constructed as follows. So we have our input, the X, the machine parameters. They are divided into two halves, X1 and X2. And then via combination of multiplication, addition, exponential functions, and those functions S and T, they are combined to get back the output, so our beam properties. And due to the special structure of those mathematical expressions, they are invertible. So if we have the forward pass, then we get the inverse pass for free. So we need to train the network only in the forward direction, and we get the inverse direction simultaneously. And here the S and T are neural networks themselves. And in principle, one could choose 4 different ones, but in our case, we decided to take only one neural network for all of those. And to guarantee the invertibility, what we need is that the input and output have the same dimension. So some padding variables are added here on either one or the other or both sides. And these are just 0 variables or low noise variables. And in addition, it can happen that the output has not so much information as is in the beginning in the input. So a latent space set is added here on the output side to account for that missing information from the input. As I told you, those affine coupling blocks, you need to split your input into 2 halves, and that the input is not always split in the same way. Therefore, you need those permutation layers in between. So that X1 and X2 are always different. So this is the basic structure of those invertible neural networks. And what is still missing now is how we first of all, the loss function, the cost function. So our loss. Here we have 5 different loss functions combined. The first one, Lx, ensures that the input follows the same distribution as our data. Then the Ly ensures that the forward model follows the data. Lz makes sure that the latent space is a Gaussian distribution, or the distribution you give before. And the Lr, the reconstruction loss, guarantees that the inverse model is good. And here the last part of the loss function guarantees you that there is not much information stored in those padding variables. So now we have the structure of the neural network, we have our cost function. Now what is still missing is how to choose all the hyperparameters. So the weights, the number of layers, the size of the layers, the activation functions, and so on. What we did in our case was that we performed some hyperparameter scan based on a grid search. But there are many options how to do that. So now we have our 2 neural networks that we are using to find our surrogate models. What is still missing are the data. And so we looked at two different accelerators, but in general, the methodology can be applied to any accelerator. One just needs to have data from a reliable model, or if possible, from the machine itself. And the first accelerator we are looking at is the Argon Wakefield accelerator. It is a premier electron accelerator with the world's highest bunch charge to carry out fundamental accelerator research with an emphasis on Wakefield acceleration. And the AWA, as it is called in short, is a linear accelerator, and it consists mainly of an electron gun. Here, several radio frequencies, and for accelerating the electrons, and magnets for keeping the beam focused. And the experiment is done after 26 meters here. So for the data set, what we used was the following input, in total 9 input variables, namely the current through the solenoids, the electron gun phase, the mean bunch energy, the peak-to-peak distance, and the laser spot size. And for the output, we had 8 variables: the mean bunch energy, the energy spread of the beam, transversal root mean square beam sizes, the transversal normalized emittance, and a correlation between the transversal position and the momentum. So in total, we had for the AWA data set 18,000 samples for training and validation, and 900 samples for testing that were created with OWLE. And here would be the list of all the hyperparameters we got for the best hyperparameter scan, but I won't go into detail here. If you're interested, you can read it in our paper afterwards. I would rather go directly to the results for the forward model. So these are the results that we got for the test set. So the set of data that had not been seen during training and validation. And here you can see, first of all, the coefficient of determination, and here the relative prediction error at 95% confidence on the test set for some quantities. And one sees here for the coefficient of determination, the R-squared value, that most of the quantities are predicted quite good, but for the emittance here, this is not really, the variance is not really captured well, and we think that it is due to the presence of angular momenta inside the solenoid region, that the emittance is not, or the variance of the emittance is not captured well. But nevertheless, as you can see here, the relative prediction error also for the emittance stays below 25% for a 95% confidence. For the other quantities, it's lower, it's below 15% relative error for all the other quantities. So this was the forward surrogate model, and the results for the invertible surrogate model. So what we did here to get those relative errors, we used first the inverse model to go from, so we gave some beam properties to the inverse model to get some machine settings, and then we used the invertible model again in the forward direction to predict from the machine settings the beam parameters, and that are the relative errors you see here. So it is clear that the relative errors are much higher than for just the forward model, because you have, you call the model twice, so the errors sum up somehow. But nevertheless, well, the errors stay below 40% for a 95% confidence. what is noticeable here is that the energy is obtained almost with perfect accuracy, with a relative error of 2% with 95% confidence. Okay, so that was the first accelerator I wanted to show you, and the second one is the cyclotron, which was used for is used for the isotope decay address experiment, a proposed very high intensity electron antineutrino source, in short called the Isodar machine. And Isodar has two primary science goals. On the one hand, sterile neutrino searches using inverse beta decay events, and on the other hand, non-standard interaction searches using electron antineutrino, electron elastic scattering events. Yeah, so the difference is mainly that it's not a linear accelerator, but a cyclotron. And for this case, we are just looking at one position in the accelerator in turn 95 here, compared to the AWA, where we had several positions which we used for the model. For the input, we have 6 different input quantities, namely the radial momenta, the injection radius, the phase of the radio frequency of the acceleration cavities, and the root mean square beam sizes at injection. And for the output, we have in total 12 quantities, so the transversal and longitudinal root mean square beam sizes, the emittances, the beam halo parameters, energy, and energy spread of the beam. And concerning the data set, we used again OWLE to create our samples. So we used 3,200 samples for training, 800 samples for validation, and 1,000 samples for testing. And here again, the list of hyperparameters, where I won't go into detail here. Concerning the results, here are the R² values, so the coefficient of determination. In the first line, here you see the result for the plane forward model, and you see except for the quantities in Z direction, all the other quantities have at least an R² value of 0.95, which is very good. And the inverse or the invertible model behaves quite similar, although the R² values are a bit smaller than for a plane forward model. So it's a bit not so good as the plane forward model. And here you see the relative prediction errors, which are very good for this model. So the best relative prediction error is for the energy, where we have at a 95% confidence a relative error of 0.02%. And the parameters that are predicted worse are the halo parameters, with still just a relative prediction error of 5.6%. And for the invertible model prediction, so for the relative error, we used again first the inverse pass and then the forward pass of the invertible model. And still for the energy, we have just a relative prediction error of 0.08% at 95% confidence. And the parameters that are predicted worst are here the halo parameters and the emittance. So summarized, we can say that the forward and the invertible model describe the two operators quite well. If we have a look at the computation time, then we see a clear advantage of the surrogate models compared to OWLE. So for the AWA, one OWLE evaluation lasts 10 minutes. One prediction with our surrogate model lasts only 21 milliseconds. And for the Isodar case, one evaluation of the model lasts for nearly 2 hours, 1.8 hours, whereas our surrogate model only needs 26 microseconds. So these surrogate models are suitable to use them for optimization, using, for example, genetic algorithm. Also, if you think of doing the optimization maybe in real time or online. So the next step is now to use our models, as I said, for optimization. And an optimization strategy, quasi state of the art, would look like this. You have some random initialization, and then you use a physics-based model like OWLE. You use an optimization algorithm like a genetic algorithm. And if you're done with your numbers of generation, then you get the Pareto front, and in the end, your optimal machine settings for the parameters you want to minimize. We will change this strategy a bit. So first of all, we replace the physics-based model with our forward surrogate model and do the optimization with random initialization in the first step. And the second approach is that we replace this random initialization with an initialization using the invertible model. Because it can happen that, for example, the operators have a good guess of which beam parameters are the optimal ones. And then we can plug those parameters into our invertible model to get some machine settings, which we use for initialization of the optimization algorithm. Okay, so and the optimization problems we are looking at are the following two. So for the AWA optimization, we want to minimize the beam parameters, beam size, emittance, and energy spread of the beam at the place where the experiment takes place, so at 26 meters. And because this was an optimization that was required for a pilot experiment performed in 2020 regarding a new scheme for electron cooling. And in addition, there are some constraints at multiple positions along the accelerator. And here you see some results. So you see the objective values plotted here for several generations. In blue, you see the results for a random initialization, and in orange, you see the results for the initialization with the invertible model. And what we see here is that the optimization initialized with the invertible model converged already almost after 10 generations, whereas for the random initialization optimization, it takes more than 100 generations to be at the same optimal configuration. If we take a closer look at the constraints here, in the bottom, then we see that the optimization finds many points outside the allowed region, so that are not feasible, but there are also many points that are inside this allowed region. And I'm mentioning this because this is quite impressive, because none of the data that were used for training or validation or testing were within this allowed region. So it's even better that the surrogate models found with the optimization some points here. And the second example for the Isodar optimization is much simpler. So we chose to minimize just the emittance and the energy spread of the beam. And as before, we use again the genetic algorithm using the forward surrogate model. here you see again the objectives for different generations, and in black you see our initial guess from the invertible model, and again orange denotes the initialization with the invertible model, and blue the random initialization. And also for this you see that already from the beginning the invertible model is nearly converged, whereas it lasts around 40 or 100 generations until the random initialized optimization is at the same level. And again, we validated our results of the optimal points here with OWLE. So what we did is we chose, in this case, only 100 points due to the computational cost, which we plugged into OWLE. So we took the machine settings, plugged it into OWLE, and the black triangles is what OWLE gave us back. So nearly all the points are within the 90% confidence region of the optimal Pareto front. And this is impressive because in gray you see the points that were used here for training and validation, and there are hardly any points here within this confidence region. Yeah, and so we see that we have for the objectives, it's on a good result. So how does it look like for in terms of speed? And here we also compare our approach of solving the optimization problem with a surrogate model instead of using OWLE to solve the same optimization problem. And for the calculation of the time to solution and computational costs, we also included the time to train the model, so including the performed hyperparameter scan. And for the AWA, we get that our approach is 3 times faster than if we would use OWLE, and we have a computational cost save of 45%. And for the Isodar example, we get that the computational cost is improved by 98%, that it is 600 times faster. So summarized, I showed you an approach for optimizing particle accelerator operations using densely connected and invertible neural networks. I showed you the construction of the networks and explained the optimization approach, and I demonstrated everything with 2 different accelerators, AWA and Isodar. But the proposed methods, of course, for building these models are general enough to be applicable to any kind of particle accelerators. And such fast surrogate models enable now maybe also online and real-time multi-objective optimization of particle accelerators. Yeah, if you want to know more details, then I refer to our paper, which you can find online, or you can also ask questions right now. Thanks a lot for your attention.